Imagine that you are a biologist and you are interested in conserving rare species of butterflies in the dense rainforest, and so you come up with few characteristics which you will be observing for these butterflies and collecting data for it. Again, the next step would be to identify the butterflies for which you will be collecting this data. Now the one way is to go and collect the data for all the butterflies thriving in this dense rainforest, which is practically impossible in terms of time and money, right? So what you do, you choose a sample out of these butterflies in the rainforest in a way that this sample is the representative of all the butterflies, right? So what are we talking about here? We are talking about three important things here. One is population, the other is sample, and the other is variable. So what is population? Population is a group of interest of study. Here in this case, population is all the butterflies which are thriving in this dense rainforest. And what is sample? Sample is a subset of this group of interest which represent this whole population, right? What is variable? Variables are the characteristic of interest which can be measured. It can be a numerical data or it can be a qualitative data. So let's say researcher collects all this data for the sample. Let's have a look at nature of these data points collected. And what we will be talking now is different kinds of variables. So let's understand different type of variables. What is exactly different type of variables is, we know that variables are the characteristics which we are studying, which we can measure. And we know that measurement can be done in terms of a number or in terms of a quality, and hence accordingly is a type of variables. This data set represents characteristics of 5 butterflies, and each row is a record which corresponds to one butterfly, and each column is a particular characteristic belonging to that butterfly. These characteristics are variables, and variables have different data types, and on broader level we have a number data type and qualitative data type. If we look at the number data variables with number data type, we will see that wingspan and number of offsprings are the ones which are representing number data type. Do you think butterfly ID is representing number? No, because it is not quantifying anything. It is just representing each butterfly, and it will fall in the category of qualitative variable, which we will be talking soon. So let's focus on numeric data type. And if we see wingspan and number of offspring, let's identify the difference between the type of quantity these variables are presenting. Can we have an offspring with the value 3.5? No, right? So there would be numeric representation, quantitative representation of number of offspring, but that is limited in number with the values which cannot be infinite in number, right? They can only be whole number values. But if we see the wingspan, and let's say we are talking about the valid range of the wingspan of butterfly, there can be infinite values literally, right? Because we can have decimal values. We can have 6.7 also, we can have 6.3 also, 7.2 also, whatever is the valid wingspan value for a butterfly, it can have infinite number of values. So these are two different kind of numeric quantitative variable types, and these kind of numeric data type is discrete data type because it is having discrete values, right? Not just any value, it has limited set of values, and these are ones which can have any values, any number of values, and this is continuous data type. Now let's move to qualitative data type. So if we see qualitative data type, we have already identified one butterfly ID. The other ones are color patterns, habitat preference, feeding habit, activity level. Now let's see color patterns. If we see color patterns, striped, spotted, solid, can we say without particular preference that one particular pattern is better than other? No. Similarly, for habitat preference and feeding habit, we cannot say that particular quality is better than the other. We cannot order these qualities, right? And these qualitative variable types which cannot be ordered are called nominal qualitative data types. While we have a look at activity level, we will say moderate is definitely better than low and high is better than moderate, and we can put them in order: moderate, low, moderate, high, right? Similarly, if we talk about shirt size, shoe size, we can order them from low, medium, large, right? Small, medium, large. So these type of variables, qualitative variables, which represent an order, are called ordinal variable types. How about butterfly ID? Is it representing an order, or is it like nominal variable? We cannot say that butterfly number 1 is better than number 2 or 3. So these are definitely nominal variable data types. So I hope we understand what are different kinds of variables: numeric and qualitative, and within numeric continuous and discrete, and within qualitative we have nominal and ordinal. Let's have a look at another data set and validate our understanding. This time we have a data set related to online ordering, and each order is a record and it has different variables associated with it, which is order ID, customer ID, product category, order date, order value, shipping country, payment method, shipping speed, customer rating, quantity. And at a first glance we can find that these variable types belongs to different category over here, right? And let's together identify the category of each variable. So order ID, let's talk about order ID. What does it represent? Is it a quantitative variable or is it a qualitative variable? It's not a quantitative variable. It is not quantifying order ID. It is a qualitative variable. It is representing a quality which is an identification of the order, right? And what kind of qualitative variable it is? Is it nominal or is it ordinal? Definitely 0, 1 is not better than 0, 2 order, right? We can't say that. So it is nominal qualitative variable. Let's talk about customer ID. Similar to order ID, and this also falls in the category of nominal variable. How about product category? Similar thing, right? Representing category of a product, quality of a product, right? Not exactly quality, one qualitative variable, right? We cannot order these in particular order to signify something, right? So these are again nominal variable. Let's talk about order date. Let's park order date. Actually, we'll come back to it. Let's talk about order value. Order value is a definitely numeric value. It is quantifying the price, and price could be anything, right? It can have a decimal value also. So it is quantitative, right? And what kind of quantitative it is? Is it continuous or discrete? It's continuous, right? So we will say it is continuous. Let's talk about shipping country. Again, it is nominal data type, and payment method for the same reason, nominal data type. Shipping speed, if we can categorize it in terms of order. Is it 2-day shipping, standard or express, right? So this is ordinal. Coming to customer rating. Customer rating, although is a number, but it is again representing a quality, and where each number is carrying a significance in the term that we can order the rating, right? So we know that 3 is better than 4. I'm sorry. 5 is better than 4, and 4 is better than 3, right? And quantity is definitely discrete quantitative, because we cannot have quantities in decimal, and it is a discrete quantitative variable. We are assuming that we are just ordering products where we are not measuring any quantity in like kilogram or something like that. It's just a number of things, right? So it is a discrete quantitative variable. And let's come back to order date. What kind of variable it is? What do you think? So order date is definitely a numeric variable, but it can be discrete, it can be continuous depending on its format. In current format, it is discrete, right? But if we would have added time to it, then it would have become continuous numeric value. Imagine a new shop has recently opened in your neighborhood, offering a variety of product ranging from clothing to accessories and footwear. Excited about the opening, you decide to visit the shop and explore what they have to offer. So as you enter into the store, you see colorful displays arranged neatly, and what curiosity sparks in your mind is, what is the pricing strategy of this shop? Are they offering some very high-end products? Are their pricing affordable by you or not? So you come up with different questions in your mind, and to answer those questions, you jot down some of the product prices. Definitely you cannot jot down the prices of all the products in the shop, so you identify few products which can represent the shop and you jot down the prices. And let's see how your questions are answered through something called measure of central tendency, which is a value which attempts to describe a particular data, and that can be done through mean, median, mode. So let's calculate these one by one and try to understand how they are representing or describing this whole set of data. Measure of central tendency, indicated by mean, median, mode, indicates central value which attempts to describe data set. Depending on the condition or different data sets, one measure becomes more appropriate than other. So let's see how we can calculate each of these and what is the context which makes them better as compared to other. So first measure of central tendency is mean, which is applicable in case of both numerical continuous and numerical discrete data. In case of sample, it is indicated by the notation x bar, and in case of population, it is indicated by the symbol mu, while the formula remains same, which is equal to sum of all the values divided by number of the values. In this case, we have 11 values, and what we have to do, we have to sum up all the values and divide by the number of values. This we can denote as x1 plus x2 plus xn divided by n, right? And it can also be indicated with the help of sigma function or summation x divided by n, right? So in our case, what is the mean of this data? It is equal to 890 upon 11, which comes around 80 point something. Now let's understand if mean here correctly indicates or represents the central value of data. If we look at the data closely, do we find any value which is near to 80? No, but it is due to this 500 value our mean is getting influenced, right? And this value is an extreme value which is also called outlier. It can be on the extreme higher side or it can be on the extreme lower side as well, and these values impact mean. And so in case the data contains extreme values, mean is not the appropriate measure. Let's try removing 500 and see if we get the appropriate value. So if I remove 500 from this, I'll be only summing up these values, right? And my values will become 10, and in that case my x bar will be equal to 390 upon 10, and it will be equal to 39. And it in this 39 value is a very close indicator of the representing or is very closely representing the data set, right? But is it right to remove outlier? Not really. It depends on the context. If you think that outlier is erroneously added, then definitely we can remove outlier. But if we are not sure, we cannot remove outlier, and it can be the case that we have not collected enough sample and that value is not really an outlier. So we need another measurement which is not impacted by this outlier, and that another measurement is median. Let's understand how median works. Let's find out the median in this case and then understand where it is applicable. So what we did, we picked up this original data of prices in the shop, right, and we arranged in the order of lowest to highest. Okay, so if you notice, these are in increasing order, from 25 as a minimum value and 500 as the maximum value. Now these values are odd in number for the reason they are total 11 in number, right? Now what is median? When we arrange these values, right, in increasing order, we arrive at the middle value. Okay, so 5 values from here and 5 values on the right side, and the middle value is 40. So in this case, median is equal to 40. In odd number case, the median value is just the middle value of the data set when the data is arranged in increasing order. Now what about even number of values? Well, let's say this is even number of values. These are total 12 in number. The middle value, we will again arrange it in increasing order, then divide the data into 2 parts, and we know that this side it is 5, this side it is 5, and these values are the middle values are 6th and 7th value. And what we do to find out the median? We do the mean of these two middle values. So we do 40 plus 42 divided by 2. In this case, median is equal to 41. If we see how the median is derived, we can clearly say that median can only be derived for the data set which can be arranged on the ordinal scale, whether it is a numeric data or whether it is a categorical data. For in case of numerical data, definitely whether it is continuous or discrete, it can be arranged from lowest to highest order. In case of categorical data, we have this ordinal data, right, categories which can be arranged if they are numbers from from lowest to highest value, right? So this is applicable on values should be measurable on ordinal scale. Now let's find how median in this case is better than mean. So in case of mean, what we found that it was influenced by the outlier. We were not sure that whether to remove this outlier or not. We need to drill down, right, if we have to remove outlier or not. Now if you have a look at this, we have median as the middle value. It has nothing to do with outlier. It is clearly not getting influenced by outlier. Now what information median is sharing? Let's say I go out of the shop and I say the median value for the prices in the data shop is 40. So what information you will derive from it is that half of the values of the prices are below 40 and half of the prices in the shop are above 40. We don't know how much it is, but we are for sure that it is below 40 and above 40, and we can derive the nature of the pricing strategy in the shop, whether it is affordable for us or not. Mode is the third measure of central tendency, and it indicates the most occurring value in the data set. Okay, although we can use it for numerical data, right? Let's say in this case of prices in the shop, we find that most occurring price is 40, right? So in this case, mode is equal to 40. So what we can deduct from here, that most of the products in the shop are priced at $40. It is mostly used in case of nominal data where there is no ordinal, right? There is no ordinal scale, there is no numerical value, and in that case we find out the most occurring value in the data set. Let's say we go and jot down the colors of different products in the shop, right? And in the sample we find that these are the colors, and what is the most occurring value here? It is red. So we conclude that most of the products in the shop are red in color. Now there can be more than one mode. Let's say we get 3 red and 3 blue. In that case we have 2 modes in the data set. So that's all about measure of central tendency. Let's have a look at these data sets. Both of them have got mean value 10. If we look at the values inside these data sets, we find 10 as a reasonable measure for the central tendency. But as the word says, central tendency indicates a central value which tries to describe data points. But yet we see these data sets are quite different from each other in the sense that the first data set has limited number of values, while the data set 2 has values spread it across. So we need another measurement apart from measurement of central tendency to understand data. That measurement is measurement of dispersion. Within measurement of dispersion, we have different kinds of measures including range, IQR, standard deviation, and variance. So let's understand these measures one by one with the help of examples. So Alice is an owner of a coffee shop. In order to make customer experience better, she starts by recording customer waiting time at the counter. She records waiting time of 10 customers in the busy morning hours. She wants to understand what is the general waiting time, how the time of the waiting varies with respect to this general waiting time of the customer. And she uses measures of dispersion to come up with the data. So let's calculate them one by one. Simplest measure of dispersion is range, which measures the difference between the highest value and the lowest value, which in this case comes out to be 15 minus 2 equal to 13. The second measure of dispersion is called IQR, which is also known as interquartile range. To arrive at interquartile range, we need to know positional measures which are called quartiles. To find out IQR and hence quartile, we need to arrange the data from lowest to highest order, like in the case of median, and then find out the median of that data. And as we know from previous lecture of measure of central tendency, these are even in number, so we have 2 middle values, and we will find the mean of these 2 middle values in order to find the median. Median is also called second quartile, Q2, median, and it divides the data into two equal halves, 50% below it and 50% above it. 50% data which is below median, we will again divide it into 2 parts. So there are 4 data points. Again we will find the median of these, and we have 3 plus 4 divided by 2 is equal to 3.5. So median of the lower half is called Q1, first quartile. Let's go to the upper half and divide it into again 2 equal parts and find the median of this. So we have 6, 7, 8, 15, and these are 4 in number, so we will find the mean of these middle values, which is 7 plus 8 upon 2 is equal to 7.5. So this is Q3 or third quartile. Let's say we have a data set which is spread it across a point. We have quartiles which divide data into 4 equal parts. So we have median in the middle, which divides the data into equal halves, and it is also known as Q2. Then we have Q1, below which we have 25% data, and below median we have 50% of data, and then we have Q3, below which we have 75% of data. Please note that Q1, Q2, Q3 are not measures of dispersion. Measure of dispersion which we will be deriving from these quartiles is IQR, which measures the spread of middle 50% of data, which is between Q3 and Q1. So we simply say IQR is equal to Q3 minus Q1. And in this case, we can say IQR is equal to 7.5 minus 3.5, which is equal to 4. So here is the IQR. Now the important point to note about IQR is that it is not influenced by outliers. So when we see range, it is definitely influenced by outlier. But when we see interquartile range, this is possibly, outliers are possibly not the middle 50% data, and so this is not influenced by outliers, and it gives us good idea of how spread data could be. While we derived IQR, we touched upon few values: minimum value in the data set, maximum value in the data set, second quartile, which is median, first quartile, and the third quartile. We came across these values, which are total 5 in number, and we call these values as 5-point summary. 5-point summary for any data set is given as minimum, Q1, Q2, which is median, Q3, and maximum. So for a given data set which we identified, it's 2, Q1 was Q1 was 3.5, Q2 was 5, and then 7.5, maximum was 15. Now we can visualize this 5-point summary with the help of a plot called box and whisker plot. So let's draw a box and whisker plot for this 5-point summary. To draw this, first we will make a line and mark our values. So we have a minimum value, we have a maximum value, so it is 2 in our case and 15 here. Then we have Q1, which is 3.5, right? Let's say somewhere here, okay, which is 3.5. And then we have Q2, which is 5, and then we have Q3, which is 7.5. So we have marked all these values. Now what we have to do, we have to make a box between Q1 to Q3. Okay, simple rectangle. Perfect. Now can you tell what this box length is representing? This is IQR, right? It is the difference between Q3 and Q1, IQR. That is what IQR is, right? And can you tell what is this min max representing? This is range, right? You have to make a whisker, okay? And to make whisker, we go till this point, okay, till the maximum point, and make a whisker like that. And similarly, in case of minimum, we make a whisker like that. Make a line which passes through Q2. So Q2 is our median, right? And this is the whisker plot. In actual visual representation, we don't need to write minimum, maximum and all. All we need is simple whisker plot, right? And with the help of whisker plot, when you have a look at whisker plot, you can immediately get the feel of how much dispersed data is, and something called skewness of data, which we'll be learning soon in some time after we covered measure of dispersion, and when we will be learning shape of distribution. We can get the skewness of data depending on the where this line is passing through. Is it passing through this side, or in the middle of the box? Okay, we'll talk about it more in some time. Very important point of the box plot is outlier identification. And for outlier identification, we need to get a couple of fences. What I mean, we get a value which lies here and here, and this value is, let's say, Q1 minus 1.5 IQR. This value is Q3 plus 1.5 IQR. Any data point beyond this point is identified as outlier. So in our case, we have IQR is equal to Q3 minus Q1, which was 4, right? Let's calculate Q1 minus 1.5 IQR, which implies 3.5 minus 1.5 into 4, and which is equal to 3.5 minus, so it comes out to be minus 3.5, and on the positive side we have Q3 plus 1.5 IQR, which comes out to be 7.5 plus 1.5 into 4, which is 7.5 plus 7, which is equal to 14.5, right? Now any data set which has value below minus 3.5 or above 14.5 is an outlier. So going by this term, is 15 an outlier? Yes, it is an outlier, but again it depends on our discretion whether we want to include it or not finally. And also to note that there is one more fence, which is like Q3 plus 3 IQR, and on this side we have Q1 minus 3 IQR. Any point below this or above these is major outlier, okay? And the rest of it in this range, they are outliers, but whether we want to include them or exclude them depends on our discretion. So if we see at box and whisker plot, that it is a very useful plot, and we'll be using it often when we'll be exploring data using Python, and when we will be visualizing dispersion through IQR. We can compare two data sets also. Let's say Alice, who is the owner of coffee shop, records waiting time for different days, Monday, Tuesday, Wednesday, for 10 customers, and draws box plot of each. Then we can do the comparison of different days, data dispersion for different days using Boxplot for each day. So this is how Boxplot is very useful, and we talked about the term skewness, which we will be talking about soon when we talk about data distribution. Let's move to next measure of dispersion, which is standard deviation. We learned about two measures of dispersion, IQR and range, with the help of which we were able to make out how spreaded our data set is. Now, with the help of variance and standard deviation, we will identify how close each data point is to the central value, and we know that the central value of a data set is mean. What we'll be doing, we'll be deriving average distance of each point from the mean. So mean value is this, and these are our data points. All right, let's make a line and let's jot down these points over here. For the sake of simplicity, for not having decimal value, for having a simple value, I'll just change this 15 to 16, and this is just for the demo purpose to show simple calculation. Okay, so our mean turns out to be 6. So what I'll do, I'll put this 6 over here. Now let's mark all the points. Below 6 we have 2, 3, 4, 5. So let's say we have 5 over here, we have 4 over here, 3 and 2 over here. Okay, and this side we have 6 itself, and then we have 7, 8, 16. Okay, because we have changed 15 to 16 for the sake of simplicity. Now let's calculate the distance of each point from the mean. So if we calculate the difference between the each point from the mean, that will be shown like this, x minus x bar, and it is also known as deviation. it's not standard deviation, it is just deviation of a point from the mean. So if we see this is 7 minus 6 and it is 1, right? Similarly here we have 2. Now when we come to this side, deviation becomes negative, right? It is minus 1 in this case, and let's say minus 2 in this case, and so on, right? So let's first make a table and jot down the value of deviations for each point. So we know that the mean here is 6. So let's quickly jot down the differences. Minus 4, minus 3, minus 2, minus 2, minus 1, minus 1, 0, 1, 2. Okay, these are the differences, and we can do the square. Now the important point to note that is that we mentioned that average distance of each point from the mean. Now we are talking about the average square distance, right, rather than talking about x minus x bar. The point is we are only bothered about magnitudes and not the sign of these distances, right? Now this could have been done with the help of absolute value also, like minus 4's absolute value is 4. But why we are not considering absolute value and we are considering square? Because of the advantages squared value have for certain reasons, in which we will be looking at when we come across future videos during regression analysis. Let's just focus over here that x minus x bar whole square is getting rid of signs of the magnitude, okay? And so we have x minus x bar whole square, and our distance is average square distance of each point from the mean. Okay, so let's write it as summation I is equal to 1 to, let's write capital N for now, okay, and we will understand summation xi minus x bar whole square divided by n, where n is the count of the values, and this is called sigma square, and this sigma square is called variance. The original point to note that is, in our case, the unit of the magnitude, which was customer waiting time in our example data, was minutes, right? So what would be the unit of variance? It will be minute square, right? In our case, we have got sample data and not the population data, right? Population in case of coffee shop would be all the customer visiting to the coffee shop, but sample is the customers visiting in the morning, first 10 customer visiting in the morning, let's say that, right? So that is the sample. This sigma square and this formula is applicable in terms of population, while for sample we have s square, and the formula changes to I is equal to 1 to n xi minus x bar square upon n minus 1. Now why n minus 1 and why not n is another question, and it is related to something called degrees of freedom, and I'll just explain it quickly. I'll not dive deep into it, just not to deviate from the topic. Let's just focus on the formula. But in general, degrees of freedom, let's say we let's understand quickly degrees of freedom. Let's say we have value a plus b plus c equal to 10, right? Or let's say we have a plus b is equal to 10. Now here we don't know both a and b, and we are free to choose one value. If we know one value, if we choose one value, then we can automatically drive other values, right? Based on a's value, we can have b's value. Similarly, in case of a plus b plus c equal to 10, if we freely choose two values, we can derive third value, right? So this is degree of freedom. So in this case, degree of freedom is 2. Now in case of sample and population, right? if we know x bar, that means we can freely choose the value of n minus 1 values in the sample to arrive at x bar, while in population it's not an estimate, right? While population is not an estimate, so there we choose n. Let's stick to the topic that variance in case of sample is this, and ours is sample and not the population. But in case you go for population data, then this is the variance. Let's talk about just sample variance. S square is equal to summation I is equal to 1 to n xi minus x bar whole square divided by n minus 1. So whatever sample variance we arrive at in this case, after calculating this, which will be sum of all this divided by 9, right? Somewhere around 120 upon 9, whatever is the calculation, this variance will be derived, and this will be in minutes square. But we wanted to, originally what we wanted to see, the average distance, not the square distance. When we are doing interpretation to see the variability of data, we cannot make out, because our original unit is minutes, or variance which we are arriving is square. So in order to make apple to apple comparison, right, what we do? We do the square root, okay, of variance, and that comes as square root of summation of I is equal to 1 to n xi minus x bar whole square divided by n minus 1, and this is also called RMSD. We perform steps in this order. First we find the deviation, this is the deviation, and then we do the square, then we find the mean, and then we do the under root. So standard deviation is interpreting how close on an average each data point is from the mean. Now let's talk about one more important point which we touched when we talk about mean. When is mean the appropriate measure? When the data is normally distributed, or we can say when the data has symmetrical distribution, or we can say there are no outliers in the data, right? Because mean is heavily influenced by outliers, and so will be the standard deviation. So we talked about interquartile range, which was derived from median in case we have asymmetrical data, right? Take the measurement in terms of IQR, and in case we have symmetrical data, we talk in terms of standard deviation and mean. So Tina is an owner of an ice cream shop called Sweet Scoops, and she wants to gain insight into the buying patterns and customer demographics of her ice cream shop in order to offer better offerings and have better marketing strategy. She comes up with the data, okay, in order to find out what are the most popular ice cream flavors among customers and how is the age of customer distributed at her shop. So she has a stable of 25 customers now, but the problem is just by looking at this data, she is not able to conclude anything, right? She wants something which can give her a better picture without juggling with this data. And let's see how we can solve her problem with the help of visual representation of data. Let's start by answering our first question: what are the most popular ice cream flavors? And what we have to do is, first we have to make a table, and that table is called frequency table. On the first column we'll write the flavors, on the second column we'll write the count of the customers who brought these flavors. For the sake of simplicity, we have three flavors. One is chocolate, then we have vanilla, then we have strawberry. Against each flavor we will count how many brought chocolate. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so 10 persons got chocolate, Similarly, we count strawberry and vanilla and it comes out to be 6 and 9. Okay, so this is frequency table, and we can see that chocolate is the most popular ice cream flavor. Now we can see it in other ways too with the help of graphical representation. There can be a pie chart where we write the percentage of each one's popularity, and with the area size one can make out which one is popular. The other way could be and the more popular way is bar graph. Let's draw a bar graph. On the x-axis we will write flavors, and on the y-axis we will write the count. Let's say we start with 5, 6, 7, 8, 9, 10. Pardon for the bad drawing. Okay, let's make a bar graph. For chocolate we have 10. For vanilla we have, okay, there it is till this point. Okay, and for strawberry we have till 9. So that was slightly bad drawing, but the point over here is to understand that we can make out with the help of height of these bar graphs that which one is the highest and has the most popular, right? In the real world there can be more complexities, there can be more flavors, there can be more data. While getting insight into the data, we need visual representation to get a quick insight and share it with stakeholders. And this is called bar graph. Bar graph is used to get insight for the qualitative variables, right? Qualitative variables, and we can use bar graph in multiple ways. Let's say we can have one more variable over here, let's say gender of the customer, and then we can break this count into count by male and then count by female, right? And then we can compare the count alongside together. So that's other way. So this is bar graph. Let's talk about how we can visualize age distribution. Now have a look at this data of age. Can we really make plot each age on the x-axis and count of each age on the y-axis? In fact, we might not be really interested in how many customer with age 25 came, how many with 32. What we may be interested in is what age groups came, like age groups in the sense from 5 to 15 or 15 to 25, right? Now this grouping may again depend on my criterias, but the gist is that we need to divide age into groups. We need something called binning to create our frequency table. Now the binning may look something like this: 0 to 10, 10 to 20, 20 to 30, and so on. And if we count, the total number comes out to be 25, because total number of customers are 25, right? All we have done is we have divided counts according to the age group they belong to. It is simplified, and it is also called frequency table, but it is for quantitative data. Now let's visualize this data with the help of histogram. To draw a histogram, again we have to take our x-axis and y-axis, and on x-axis mark age groups. Let's say 0, 10. This binning could differ in terms of the width of the group and the boundaries of the group, depending on what kind of insight we are looking for. But for now, let's just keep it this. And what we have to do, we have to mark frequency or the count of customers on y-axis. Let's keep it till 6, as we see maximum is 6. Now to draw a histogram. What we'll do, we'll make a rectangle which has width equal to the class interval. So this is also called class interval or width. Take the height of the rectangle which we are drawing according to the frequency of the age group. Let's say we have frequency of this class interval as 5. So we will make a rectangle. Okay, so this is our rectangle. Now, so if I ask you, what does the area representing, right? Which rectangle will have more area? The one which has the higher frequency, because we have fixed class interval, right? Now let's make another rectangle on the same lines. So for 20 to 20 we will make a rectangle starting from 10. and going till 20, its height goes till 4. Let's complete the rectangles. Peak goes in the interval 20 to 30. It implies that people in the age group 20 to 30 are largest in number. Definitely, when we have a look at it, we can interpret many things, like, let's say for example, which is the highest customer, which group is the highest customer base. Then we can also interpret how many customers we have below the age, let's say 40. And this can also be derived with the help of something called cumulative frequency. Let's enhance our table. So we can make histogram either against frequency, which gives us the exact count of the age group, customers belonging to particular age group, or we can make histogram against two other kind of frequencies, which is relative frequency and the other is cumulative frequency. So what is relative frequency? So if we see the age group 0 to 10, it has frequency, that is number of customers belonging to this age group, as 5. And what is the total number of customers? It is 25, and we get 0.2 or 20%, right? So we have this as 0.2. Similarly, we can find the relative frequency for other age groups, and we can draw our histogram against relative frequency on the y-axis and again age group on the x-axis, or we can draw against cumulative frequency. So cumulative frequency, as the word says, cumulative. For age group 0 to 10 we have 5, and for age group 10 to 20 we have 4 till we have 9. So what we are doing, we in particular age group we will sum up the frequencies preceding and that particular frequency. So what does that mean? That customers, since we are excluding the upper boundary, customer below age group 20 are equal to the relative frequency, right? And we can visualize that data. As we have learned in the past, we can visualize distributions related to frequency or number of occurrences of data in a data set using histogram. We can obtain different kind of histograms based on nature of data. They can be symmetrical or asymmetrical in nature. They can be unimodal or bimodal, or in other terms have different number of peaks within that data set. We can form a shape of distribution on the basis of these histograms. Now, why this shape of histogram is important? Just by having a look at the shape of distribution, we can understand the spread and behavior of a given distribution. And this visual representation helps us and others to understand behavior of the data visually, and hence it comes very handy when reporting observation to the stakeholders. We can arrive at estimated mean, median, mode using these shapes of distribution, and hence they form a very important concept. Descriptive statistics easy. Let's look at the data of height of 100 adult males in centimeter, and if we look at this distribution, we can see that it is symmetrical distribution. So what is symmetrical distribution? If I draw a line here, I can divide these two parts into equal halves, which are mirror images of each other, and the shape of distribution which will be formed with symmetrical distribution is somewhere like this. How can we estimate mean, median, mode with a symmetrical distribution? Now we know that mean is the central value of the distribution, and we can clearly see in case of symmetrical distribution, center value lies somewhere between 175 to 180 centimeter. Mean in case of central distribution is lying over here. Similarly, in case of median or symmetrical distribution, we know that median divides the data into two equal halves, and clearly it is also lying at the central position. Median will also be at the same position. How about mode? Mode shows the peak of occurrence, highest number of occurrences in a data set, right? And clearly highest number of occurrences are where the peak is. So again, mode is again at this data set. We can safely say that in symmetrical data distribution, mean is equal to median is equal to mode. Now by visually looking at the symmetrical distribution, we can estimate mean, median, mode, and for the actual calculation definitely we need to use calculator, but when we are sharing this visuals with stakeholders, all we need is estimation. By having a look at this visualization, we can also make certain inferences about the spread of data. First of all, data is equally spreaded from the central location, but then it can be a narrow symmetrical distribution or it can be a wider symmetrical distribution. If it is narrow symmetrical distribution, that would imply that most of the values are located around central value. There is less spread of data or less variability in the data. While in case of wider symmetrical distribution, we can clearly see that there is a lot of variability in the data. The data points are spread. That means in this case, adult male heights have lot of variation. But if it is narrow, then we can say that adult male heights are somewhere around 175 to 80, little less or little more than that. This is about the interpretation or inferences drawn from the visual. If we want to make actual calculation for the variability, we need to arrive at standard deviation and interquartile range, which we have already discussed using Boxplot and calculation. Let's move to next kind of asymmetrical distributions, which are also called skewed distribution, and we have two kind of skewed distribution. One is positively skewed and the other is negatively skewed. So we saw in case of symmetrical distribution, graph appears symmetrical, which means that there are as many data values on the left side of the median as on the right side. But in case of skewed distribution, we say data is skewed when the curve appears distorted either to the left or the right in statistical distribution. Important point to note in case of skewed data is that it represents the direction of outliers. Although it does not tell us about the number of outliers, it tells us the direction, that in which direction outliers are residing. So by having a look at this graph, we can say outliers are residing in this direction, in left direction or negative direction, while in this case we can clearly say that outliers are residing in positive direction, and hence is the name. So this is left skewed, or we can also call it as negatively skewed, and this is right skewed, and we also call it positively skewed distribution. So let's just talk about one positive skewed distribution example first. So if we look at this graph of income distribution in $1,000 within a company, we'll see that most of the employees lie in the lower range side, and then on the higher end we have less number of employees. Although this might not be the ideal distribution, this is just to portray the positively skewed distribution, and hence this curve forms a shape something like this. Now how about deciding or estimating mean, median, mode with the help of this? Again, the definition of mean, median, mode remains same. Mode is the highest number of occurrences, so it will always occur at the peak. And median also definition remains same. Whatever is the data, right, from here to here, it will always be the middle point of the data set. So let's say our median is this. And how about mean? When the outliers are this side, we know that mean is heavily influenced by outliers, and it tends to be whatever is the value of outlier, it tends to be going towards that. So our mean will reside towards outlier, and in this case we can see that mean in case of positively skewed is greater than median is greater than mode. And just by having a look at visualization, we can estimate mean, median, mode, although we cannot calculate the exact value, which we might not need. And spreadability, we have already talked about that data spreads in this direction with outliers residing in this side. This was about positive skewed distribution. Let's talk about negatively skewed distribution. Let's talk about another kind of asymmetrical distribution, which is negatively skewed data distribution, or also left skewed data distribution. As we already talked that outliers tend to be towards left side. So graph appears distorted in this manner. So let's take an example of scores of an easy exam in a class where most of the students get marks in higher range, right? And the number of students getting lower marks tends to decrease. This is an example of scores of an easy exam in a class. So this forms a data distribution which appears to be negatively skewed. Now if we have to find or estimate the mean, median, mode, we will follow the similar lines which we did in case of positively skewed, and we know the definition remains same. Mode is the highest number of values. Okay, so this side peak is occurring, and so mode remains on this side. Median is the value which divides the data into equal halves, so we have where median occurring over here, and mean tends to be towards where outliers are. Mean will appear over here, so we will have median and mean. So in case of negatively skewed data, we have clearly mean less than median less than mode. Perfect example of visualization where we can interpret and estimate the central tendency and dispersion of data. Let's move to our last kind of distribution, which is on the basis of actually number of peaks occurring in the data distribution. Distribution can also be seen from the perspective of number of modes in the distribution, like we have been seeing so far. Only one single mode distribution, and they are also called unimodal distribution. In case we have bimodal distribution where we have 2 times number of peaks are occurring, and it is bimodal, and of course we can have more than 2 modes where peak occurs multiple times, and that would be multimodal distribution. Now let's see this example where we have a manipulated data of commute time to the office, and one peak occurs at the time duration of 11 to 20 minutes. Number of employees who commute within this time duration is high, and similarly there can also be the case when number of employees who commute within the time of 61 to 70 minutes is also high. What we can infer for mean, median, mode over here, definitely we have 2 modes over here, this value and this value. How about mean? Mean definitely tends to shift towards the peaks, right? And in this case it is not certainly the right measure of distribution or central tendency of data, so we will say mean is not the right measure. How about median? Median is clearly the best indicator to indicate central location of a data, and it is less affected by the peaks, right? So that was all about different kinds of distribution, symmetrical, asymmetrical, and in terms of modal distribution.